Alright, on the second day that we're evaluating these limits algebraically or analytically, either way is correct, we're going to be looking at those same strategies that we used the other day. We're just going to be looking at some different ways to simplify some different functions other than just factoring. So the first problems I have today have an absolute value in them. And what we're going to be doing is we're going to find the limit as x approaches 3 from the right of this function right here. Now, if you notice, direct substitution does not work. We have to figure out a way to simplify an absolute value. Well, there's two parts to the absolute value, and what I'm going to do to kind of help explain this is I'm going to draw a quick picture of just this portion. That portion of the graph, the bottom part of the function, looks like this. It's a V, it has a vertex here at 3, 0, and what it has is it has a part that's positive before you take the absolute value, and it has a part that's negative before you take the absolute value, and those are what we have to think about. This section right here is numbers like 4 and 5, so from the right, that's what we're talking about. We're going to plug in 5 and 4 and so on and so forth. Notice the type of number I get inside the absolute value before I take the absolute value. That number, 5 minus 3 is 2, it's positive. 4 minus 3 is 1, it's positive. So we're talking about the positive portion of x minus 3. The top is factorable, x minus 3, x plus 3, and the bottom, we're just going to write it as x minus 3 without the absolute value because the absolute value was not actually necessary for numbers to the right of 3. What I can do now is simplify, and I can use direct substitution at this point because I've simplified and I come up with the answer of 6. Now for the second part of this, it says find the limit as x approaches 3 from the left. Well, those numbers would be numbers like 2 and 1. Notice when you're plugging in 2, you get negative 1. When you plug in 1, you get negative 2. So you're talking about the negative portion of the absolute value. So what we're going to do is simplify the top again by factoring. And then the bottom, we're going to write the negative portion of this absolute value. So we can actually express this absolute value as negative x minus 3. Because those numbers, when you plug 2 in, gives you a negative before you take the absolute value. So now when you go ahead and reduce, we'll come up with the answer through direct substitution of 6 over negative 1, which is a negative 6. The last example on this slide has to do with square roots, and when I plug in 1, I get 0 on the bottom. So I've got to figure out a way to simplify this. And the way we're going to do that is using conjugates. What a conjugate is that you keep the two terms that are there, but you change the sign between them. If it was minus, it's now plus. If it was plus, it's minus. Okay, so I'm going to multiply the top times its conjugate. And what happens is I end up getting first times first is 1. Outer terms give me a square root of x. Inner terms give me a negative square root of x. And last times last gives me a minus x. Now, if you're good with conjugates, you realize that the whole point of them is that the middle terms drop out. So you have 1 minus x times 1 plus square root of x on the bottom. It really is a waste of time to multiply these out, and I'll show you why here in a minute. Doing enough of these problems, you will learn not to multiply those out. So on the top I have 1 minus x. On the bottom I have 1 minus x times 1 plus square root of x. Hopefully now you can see I do want to just go ahead and cancel, and that's one of the reasons I didn't multiply out the bottom. Now I can use direct substitution and plug 1 in. So I have 1 plus the square root of 1, and that gives me 1/2 as my solution. In this next problem, I notice that it is factorable on the bottom, x minus 3, x plus 3. The problem is, though, is that it doesn't match the top exactly, So what I'm going to have to do is factor out a negative on the top. When I factor out a negative on the top, I get negative 3 plus x. So when I rewrite this problem, I get negative, and this is x minus 3, all over x minus 3 times x plus 3. And now I can cancel those two out. Plug in my 3, and I get negative 1 over 3 plus 3, which is a negative 1/6. Alright, let's try another one of those that we just did in the last video. And again, when I plug in 0, I get 0 on the bottom, so I know I have to simplify. I'm going to simplify using the conjugate. So I'm going to multiply by the conjugate, keeping the same two terms, but just changing the sign between them. And I'm going to multiply the bottom by the conjugate as well, because whatever I do to the top, I have to do to the bottom. And we're ready to go through this process. On the top, then, I have first times first, which would be 2 plus x. And then I'd have my inner and my outer terms fall out, minus the square root of 2 times square root of 2, which is just a plain old 2, all over x times the square root of 2 minus x, 2 plus x, plus the square root of 2. On the top, then, I have 2 plus x minus 2, so these cancel. And now I can cancel my x's. And so when I go to plug in and use direct substitution, I get 1 over the square root of 2 plus the square root of 2, which gives me the answer of 1 over 2 square root of 2. These are some of the limits that we're going to have to memorize. They've been derived by someone else, and we just need to memorize them. So anytime we have the limit as x approaches 0 in all three of these cases, and we have the sign of x over x, we're going to know the answer is 1. Or if we have the reciprocal of that, it's still 1. Or if we have 1 minus cosine x over x is equal to 0. So we're going to use those concepts some in these next problems. Sometimes we won't use them. This one is the x to the fifth, and so you might have some difficulty factoring that. So what we're going to want to do is go ahead and divide this out. Now I'm going to use what's called synthetic division. Some of you may have forgotten about this from Algebra 2, or maybe have not been introduced to this, so this might be something we need to discuss. But what goes inside the box is what we're dividing by. What creates 0 down here, which would be a 2. I want to divide by a factor of 2. And then I'd write my coefficients for the top part across the top. Now I have a 1 coefficient for the x to the fifth. I have a 0 for the x to the fourth, a 0 for the x to the third, a 0 for the x to the second, a 0 for the x, and then a negative 32. So this is my x to the fourth, x to the third, x to the second, my x, and my constant. You have to fill in all those zeros. In synthetic division, you should end up with a 0 here if it is a factor. So we bring down the 1. 1 times 2 is 2, and then you add these together and you get 2. 2 times 2 is 4. You add those together. 4 times 2 is 8. You add these together. 8 times 2 is 16. Add these together. 16 times 2 is 32. Add them together and get 0. So your new function is 16 plus, I'm reading it backwards, 8x plus 4x squared plus 2x cubed plus x to the fourth. So each of these become your new coefficient. So this limit is going to be written once you've canceled those, because we've divided it, as x to the fourth plus 2x cubed plus 4x squared plus 8x plus 16. Now I can use direct substitution to come up with the answer. So 2 to the fourth is 16. 2 to the third is 8 times 2 is 16. 2 to the second is 4. 4 times 4 is 16. 2 times 8 is 16 plus another 16. So I have basically 16 times 5, and I come up with the answer of 80. The second one here, we're going to have to refer back to what we're supposed to memorize. I'll be using this limit right here. what I have is a scalar multiple, and we learned in the other day that we can pull that out front. So we have 3 times the limit as x approaches 0 of 1 minus cosine x over x. So really what I have is 3 times 0 because that's what this limit is equal to. So my answer is 0. Alright, for this next problem here, it's going to have to simplify in some way, shape, or form because when I plug in 0, I get 0 on the bottom, so I can't find the limit. So what I'm going to do is look at what is the tangent, and the tangent is really sine of x over cosine of x, and that would all be over x. So now on top, my cosines will actually cancel out, and I end up with the limit as x approaches 0 of sine of x over x. And from earlier in our notes, we learned that we're supposed to memorize that, and it equals 1. This next one here, I get 0 on the bottom. That's a bit of a problem. One of the things that is given here is that we're supposed to have x's. Now, that's not necessarily the case. When you have a function like this, you could have sine of 3x over 3x, and that still equals 1. You could have sine of 5x over 5x, and that still equals 1. These two things just have to be the same, whatever those x values are. So on this problem right here, if I could just make this say sine of 3t over 3t, I would be done. But it doesn't just say that. So I've got to figure out how I can make it say that. So right now I'm going to get rid of that part, and I'm going to separate these two into two different fractions. Then what I'm going to do is I'm going to say, well, if I multiply this by 3t, because I really want a 3t down here, that means I have to multiply the top by 3t, and I can do that. Then I'm going to do some rearranging here. So I'm going to rearrange, and I'm going to put this 3t right here, and I'm going to move this 3t out front. So I'm going to have a 3t over 2t times the sine of 3t over 3t. What happens now is those t's cancel, and I end up with a scalar multiple of 3/2 that can come out front. And I now can simplify this because I know this limit to be 1. And then my scalar multiple just gets multiplied back through, and I come up with my answer of 3/2. Now that is a bit confusing. You may need to listen to that more than one time. You may need to write some notes. The squeeze theorem is the last thing I'm going to be talking about in this section, and the squeeze theorem says this. If you have a function that's less than or equal to f of x that's less than or equal to another function, for all x in an open interval containing c, except possibly c itself, and if you know the limit as it approaches c of f of x as L, and the limit as x approaches c of g of x as L, well, we now can say that f of x is also equal to L because it's squeezed in between those. I want to just mention that the squeeze theorem was what was used to find today's limits that we memorized. So what we're going to do is we're going to use the squeeze theorem to find the limit as x approaches c. C happens to be in this problem 0. So what we're going to do is we're going to write the limit as x approaches 0 of this first function. And I'm going to write less than or equal to the limit as x approaches 0 of f of x. So all I'm doing is I'm putting the limit as x approaches 0 in front of each part of these because that's what I'm doing with the squeeze theorem. Then I'm going to just use direct substitution. So on this one I get 4, and this one doesn't give me anything because it's just recopying, and then this one gives me 4 again, 4 plus 0, which is 4. So therefore, by squeeze theorem, the limit as x approaches 0 of f of x is also equal to 4. It may be easier to see this in a picture, and I'm going to show you that before I end this video of what this picture really looks like. This says I'm 4 up, 1, 2, 3, 4, and it's a parabola that goes down. And this one says it's 4 up, but it goes up this direction. And they do touch each other right here at 0, 4. So you can see why the squeeze theorem works, because what you're doing is you're squeezing in between here, okay? And so the limit of this other function that falls between here has to be 4 because they touch at 0, 4.